Efficiency is often treated as the ultimate engineering goal: better fuel economy, lower energy loss, faster computation, lighter structures. On paper, more efficiency always looks like progress, but in real engineering, reliability often takes priority. Designers regularly step back from peak performance to make systems more durable, stable, and predictable. In this video, we'll examine real-world examples of that trade-off and the engineering logic behind it. At its core, reliability refers to the probability that a system will perform its intended function for a specified period under defined conditions. Engineers quantify reliability using statistical models such as failure rate distributions and mean time between failures. Efficiency, by contrast, measures how effectively input energy or resources are converted into useful output. While efficiency can often be optimized through tighter tolerances or reduced safety margins, such optimization can increase stress, temperature, or wear, ultimately reducing system lifespan. Consider thermal efficiency in combustion engines. Increasing compression ratio improves thermodynamic efficiency according to the ideal Otto-cycle relationship. However, higher compression increases peak cylinder pressures and temperatures. These conditions accelerate material fatigue, increase knock risk, and demand stronger components. Engineers therefore select compression ratios that balance fuel efficiency gains against durability constraints. The resulting design is not the most efficient possible configuration, but one that can withstand years of operation without catastrophic failure. Power electronics offer another example. Engineers can make a system smaller and more compact by running semiconductor devices closer to their maximum voltage and current limits. That can improve power density and reduce the number of parts needed. But there is a cost. Semiconductors become less reliable as they get hotter. Even a modest increase in temperature at the device's active region, called the junction, can shorten its service life quite sharply. In many cases, the relationship is not linear but steep, meaning a small temperature rise can cause a large drop in expected lifetime. That is why designers often use components below their theoretical maximum ratings. The result may be slightly lower efficiency, but it usually leads to longer-term reliability. The early jet age is a perfect example of what happens when performance outruns reliability. Engineers in the mid-20th century built engines that delivered remarkable thrust, but many of those early turbine blades failed under the intense heat and stress inside the engine. At the time, engineers had not yet fully understood two critical failure mechanisms: creep and fatigue. Creep is what happens when a material slowly deforms because it spends too long under high temperature. Fatigue is the damage that builds up when a part is stressed over and over again through repeated operating cycles. Once those mechanisms became better understood, design philosophy changed. Engineers backed away from the most extreme operating conditions or added sophisticated cooling to protect the blades. That meant giving up a little peak efficiency in order to gain something more important: an engine that could survive real service. Electrical grid infrastructure demonstrates reliability prioritization on a large scale. Transmission lines could theoretically operate closer to their thermal limits to maximize power transfer efficiency. However, environmental conditions such as ambient temperature and wind variability introduce uncertainty. Overloading lines increases sag and risk of failure. Grid operators maintain conservative margins to prevent cascading outages. The 2003 Northeast blackout highlighted how stressed systems operating near limits can propagate failures rapidly. Reliability margins exist precisely to prevent such systemic collapse. In aerospace, reliability is paramount. Aircraft engines are not operated at maximum possible temperature or thrust continuously, because doing so would accelerate wear and reduce maintenance intervals. Instead, engines are designed to operate efficiently within a controlled envelope. Maintenance schedules are based on probabilistic life modeling, including fatigue crack growth analysis. Slight efficiency sacrifices are acceptable when weighed against passenger safety and fleet reliability. An aircraft grounded for unscheduled maintenance costs far more than marginal fuel inefficiency. Software systems reveal a similar trade-off. A piece of code can be heavily optimized to run faster or use fewer computing resources, but that often makes it more complex. And once complexity goes up, readability usually goes down. That matters because software is not only built to run, it also has to be understood, debugged, updated, and maintained over time. A highly efficient system that is difficult to trace or repair can create more problems than it solves. For that reason, engineers often choose simpler architectures that use slightly more memory, processing power, or storage, but are easier to understand and easier to troubleshoot. The same logic appears in distributed systems, where redundancy is added on purpose. Running multiple servers may be less efficient in terms of energy and hardware use, but it makes the system far more resilient by reducing the risk of outages and keeping services available when one part fails. Reliability considerations also shape battery management systems in electric vehicles. Charging a battery at the highest possible rate makes charging stops shorter, but faster charging also creates more heat and places greater stress on the battery cells. Over time, that stress makes the battery lose capacity sooner and deliver less consistent performance. Manufacturers therefore limit charging curves to preserve long-term battery health. This choice sacrifices short-term efficiency in favor of sustained performance over thousands of cycles, which is what customers value more than extreme but short-lived performance. Boundary conditions further explain this prioritization. Efficiency gains often exhibit diminishing returns. Pushing a system from 90 to 95% efficiency may require disproportionately higher stress, tighter tolerances, or exotic materials. Each incremental gain may reduce margin for error. That means less room for temperature swings, wear, variation in parts, or unexpected real-world conditions. So engineers have to ask a practical question. Is that extra performance really worth the added risk? Very often, the answer is no. Operating slightly below the theoretical optimum may look less impressive on paper, but across the full life of a product, it often delivers the better result in cost, durability, and dependable performance. Failure mode analysis reinforces this perspective. Systems designed near their limits are more sensitive to variability in manufacturing, environmental conditions, or user behavior. Small deviations can produce disproportionate consequences. By contrast, systems with built-in margin tolerate variability more gracefully. This resilience is particularly valuable in environments where operating conditions are uncertain or harsh. Reliability therefore acts as a buffer against real-world unpredictability. Across industries, engineers routinely accept small efficiency penalties to ensure continuous operation. But that does not mean reliability should be pushed without limit. Extra material adds weight. Additional backup systems increase cost and complexity. Too much redundancy can make a product less competitive, less efficient, or simply too expensive to justify. So the real engineering task is not to maximize margin at all costs. It is to find the right margin for the job. Or in other words, good engineering is not about treating every system the same. It is about matching reliability, efficiency, cost, and sustainability to the real demands of the application. Modern engineering increasingly uses probabilistic risk assessment to quantify these trade-offs. They look at failure distributions, stress cycles, temperature histories, and other factors that influence how a system ages over time. That makes it possible to predict expected service life at different efficiency levels. This data-driven approach replaces intuition with statistical evidence. For example, a designer may be able to show that lowering operating temperature by only a few degrees could dramatically extend the life of a component. Once the numbers are visible, the trade-off becomes much clearer. Ultimately, engineers prioritize reliability because systems exist to deliver consistent service. Efficiency gains are meaningful only if the system continues to function. a power plant that operates at maximum theoretical efficiency but experiences frequent outages undermines its purpose. A consumer device that fails prematurely erodes trust and increases waste. Reliability sustains value over time. This does not mean efficiency is unimportant. Rather, efficiency is pursued within reliability constraints. The most successful engineering systems achieve high efficiency while preserving acceptable safety margins and predictable lifespans. Engineers understand that durability, maintainability, and resilience define long-term performance more than peak laboratory metrics. When we examine modern engineering systems through this lens, design decisions that once seemed conservative appear rational. Margins are not inefficiencies. They are deliberate safeguards. Reliability is not the enemy of performance. It is the foundation upon which sustainable performance is built. If you value precise, research-driven explanations of how engineering decisions are shaped by real-world constraints, consider subscribing to Engineering Manual for future technical explorations.